I'm going to take a look at lenses with you now. We probably all know that there are lenses in our eyes, there are lenses in cameras, and lenses in telescopes and binoculars. They're all over the place in terms of optical lenses. There are two kinds of lens. You have a lens which will cause the light to converge, or a convex lens. You have lenses which will cause the light to diverge, spread out, or concave lenses. Two types of lens, and we're going to look at both. But before we get into too much detail, let's define a few terms that we need. So, the optical center of our lens is the center of the lens. Absolutely in the middle. Principal axis is a horizontal line. It will almost always be horizontal in our diagrams. Through the optical center. You'll see in a moment when I draw the diagram. Principal focus. Well, rays entering the lens parallel to the principal axis leave the lens through the principal focus. And this should be LE. Principal focus. And vice versa. Rays which enter through the principal focus leave parallel. One of those beautiful symmetries in physics. The focal length, that is the distance between the principal focus and the optical center. This point 2f is a point 2 times the focal length from the optical center. A real image is one where rays of light actually meet to form it. And a virtual image is formed where rays of light appear to meet but don't. Or appear to originate from. Would be a virtual object, I suppose. And finally then, magnification would be your image height, how big your image is, divided by your object height. Or image distance, how far the image is from the lens, over object distance. So those are some key terms that you need to have in your mind. You need to know these. So moving on from the key terms then, let's look at the symbols. There are two kinds of lens and there are two symbols. So this is what a convex lens might actually look like. You can imagine that in 3 dimensions. This is the symbol for it. So this is a converging lens. A ray of light which comes in here will bend like this. A ray of light which comes in through the focus will come out parallel to the principal axis. This is what a concave lens might look like. Cave, bending inwards. And this is the symbol for it. Notice the difference between this, where your UV is that way up, and this. So the difference between the convex symbol and the concave symbol is the direction of the arrowheads on the ends of the line. This is meant to indicate the divergence of the light as it passes through the lens, whereas this represents the convergence of the light going through the lens. So I talked about all these definitions here. Optical center, principal axis, principal focus, focal length, 2f, all of these things. Let's now look at a diagram to put all that together. So here I have, hopefully you can spot, a convex lens because I've got these arrows like this. If it was concave, they'd be like that. I have a point here, some distance from the optical center, which is the middle of my lens. If you can imagine, if I place another dagger over the top, my convex lens might look like that, and there's the middle of it, right? This is the distance from the optical center to one focal length away. This is the principal focus. This distance is the focal length. And there's a principal focus on each side of the lens and a point 2f twice as far away on each side of the lens. This line here, which goes horizontally through the optical center, that's the principal axis. This is my optical center, which we called O. This is my focal length. This is 2f, which is twice as far away from here as the principal focus. So that's all of those definitions pretty much combined into one diagram. Principal axis, which runs horizontally through the optical center, which is the middle of the lens. We have points F, which is one focal length away from the optical center, and F is defined as the point where if a ray comes in parallel to the principal axis, it comes out through the focus. If the ray comes in through the focus, it comes out parallel to the principal axis. That's how the principal focus is defined. It is the point through which rays would enter the lens parallel to the principal axis. It's the point through which they come out. It's also the point that if they enter the lens by passing through the principal focus, they will come out parallel. That's the definition. But it is one focal length away from the optical center. So you can imagine if there were lots of rays coming in parallel to the principal axis, they'd all come out through here. They'd all be focused on this one point. right? So that's those definitions kind of in one diagram. Now, we have some special rays that allow us to draw our ray diagrams, and we've already seen two of them. If a ray comes in through the principal focus, it will come out parallel to the principal axis. If the ray comes in parallel to the principal axis, it will come out through the focus. So if you like, these are kind of mirror images of each other. If it comes in through the focus, it comes out parallel. If it comes in parallel, it comes out through the principal focus. The other special ray is one which comes in through the optical centre. If it passes in through the optical centre, it doesn't change direction. Now, if you think all you need are two rays for you to decide where your image is going to be. So these two rays here, one in parallel out through the focus, one in through the focus out parallel, where those two rays meet, that's where my image is going to be. Let's look then at ray diagrams. Now you'll notice that I've moved to graph paper now. These diagrams are amongst a small group of diagrams that you must draw really, really accurately. If you don't draw them accurately, you end up with the wrong answer. So here we have a principal axis running through the optical centre of a convex lens, because we have the arrows pointing the way they are, outwards rather than inwards. So if we stick some labels on this, I have chosen one big square as my focal length. Doesn't matter what the scale is, but you'll notice that 2f is two big squares out from the optical centre. Now, in broad terms, our object, the thing that we're looking at through the lens, could be outside 2f, at 2f, between f and 2f, at f, or inside f. Of course, there's some variation there for those positions, but basically you've got this region and right here, this region and right here, and this region. So if we start with outside 2f, let's use a couple of our special rays. Let's take a ray which comes in parallel to our principal axis. And then, because it comes in parallel, it will come out through the principal focus. So there we have one of our special rays. If we then take another of our special rays, let's say we take one that runs from the object through the optical centre, which is there, and then we run our ray down like that. I missed slightly. I should have had that absolutely on the optical centre. There we go. So where those two rays meet, that is where my image forms. Right there. So let me just change colours so that the image is really obvious. So what have we got then? We have an image which forms where two real rays of light have converged to form it. Right? Notice arrows on the rays. Now, this is the top of my object. We represent our objects by arrows, and we take rays from the top of the object. Clearly, there'd be rays from every point on the object, but if we take rays from a single point at the top, then we know where the top of the image is. And you can see the image here is upside down. So, what have we got? This image is inverted. So, we could write that down. Image properties. It is inverted. It's real because rays of light have actually met to form it. It is reduced, or it is smaller than the object, and it is between f and 2f. That's where it is. So there's one of our ray diagrams. You need to be able to draw this. Now, if you draw it really accurately, then you can measure the height of your object. You know, that might be 5 centimeters. And you can look here and you can see that's 2.5. That's half of that. So you can measure and work out the magnification of this lens. Image over object height, image over object distance would be the same. You see you've got 30 small squares here and 15 small squares here. So by drawing this really, really accurately, then we can take measurements from the diagram and work out the magnification. So there's our object outside 2f. So let's then move to an object at 2f and do the same thing. So we have a ray coming in parallel to the principal axis. Which comes out through the focus. We have a ray which comes in through the optical centre. Now, I could choose to take one through the principal focus as well. Why don't we do that? There's a ray which comes in through the principal focus, which then comes out through the principal axis. Sorry, parallel to the principal axis. And you can see that my image is formed at 2f. Just there. Just in the right place. The line isn't staying quite where I want it. So again, what have we got? We have our image here. We have our rays here. So what have we got? Well, this is 5 little squares high and this is 5 little squares high. So it is the same size as the object. It is inverted again. It is real. It's at 2f. So we had that object out here, which was forming an image in here. Now we've moved our object in and the image has moved out. See the pattern? So they're both real so far. They're both inverted so far. It was smaller when the object was outside 2f. The image was smaller. Now it's the same size. What do you think is going to happen after that? Well, let's have a look. So we have an object between F and 2F then. Let's do that and do the same process where we have a ray which comes in parallel. Now I don't have a lot of variety here. I've got 3 special rays that I can use. There's one, comes in parallel to the principal axis, comes out through the focus, principal focus. We have another ray. This time maybe we'll take it in through the optical center. We took it in through F last time. We'll take it into the optical center this time. Let's try and get in exactly the right place. It's actually easier to do this on paper. So there we go. There's our rays and our image then forms where those rays meet. So if we get that just there and we move that to there, I think that's about right. Looks about right to me. So now that's where our image is. So what have we got? Well, our image is real because real rays of light have met to form it. It's inverted because it's upside down. It is magnified rather than being reduced. And it's outside 2F. So when the object was out here, the image was here, between F and 2F. It was real, inverted, and smaller than the object. Move the object in, the image moves out. It's still real, it's still inverted. It's the same size as the object and at 2F. Move the object in further, now between F and 2F. The image is still real, still inverted. It has moved out, so as we move the object in, the image is moving out and getting bigger. And it's real and it's inverted. That pattern doesn't absolutely hold, but it holds for almost all of them. So you see the pattern forming. Remember the pattern. So that was an object between F and 2F. 2 more to do. An object at F and an object inside F. So the object at F then, remember our object, our image, sorry, was moving out, and it's already got as far out as it can go, right? So let's look at what our 2 special rays do now. So a ray which comes in parallel to the principal axis. Comes out through the focus. And a ray which comes in through the optical center. It doesn't really matter what we do here. We don't have any choice actually, because if you think about it, it's not possible to have a ray coming in through the focus. You can see those rays are parallel. So this image will be real. If it could form, real rays of light would meet to form it. And if you can imagine going as far away as you possibly can from this lens, those rays would form an image at infinity. So it feels a bit of a fudge at infinity, but real rays of light, if they ever did meet, if you can imagine going far enough away they were to converge eventually, they would converge at infinity and you'd have a real image. So, and you can imagine it's going to be an awful lot bigger than the object. But real and at infinity will do, and the pattern is getting bigger. So it would be inverted and it would be enlarged, magnified. Our final image then, our final one, is the object inside F. So again, let's do our special rays and see where that takes us. So there we have a ray coming in parallel to the principal axis, comes out through the focus, now I'm going to dot this back, you'll see why in a minute. That's where that ray appears to come from. And then if we had one which came in through the optical center, now you can see that these rays are now diverging. So there's the ray of light that actually enters and leaves the lens, and it appears to come from there. So now our image appears to be right there. Now notice I am using dotted lines for where the ray appears to go, where the image appears to form. So here we have a virtual upright, as opposed to being inverted, enlarged or magnified, behind the object. So here we have the only upright image formed in a convex lens. It is upright, it is magnified, and it's behind the object. So if your eye was down here, looking through this lens at this object, you would see an enlarged upright image. So this then, where the object is inside the principal focus of a convex lens, that is a magnifying glass. So you've got then 1, 2, 3, 4, 5 ray diagrams for the convex lens. They're all drawn using 2 of the 3 special rays we talked about, and there's only one of these ray diagrams that gives you an upright virtual image. That's a magnifying glass. all the others are inverted and they are real. So that's your convex lens. Let's then look at a concave lens. So here we have our concave lens. Let me just get rid of my convex lens because that's in there too. So there's my concave lens, and here I have my object. Now, I didn't talk about special rays for this one, should have done really, but they kind of make sense. With a converging lens, a ray which comes in parallel to the principal axis with a converging lens, convex lens, that ray will converge through the focus. With a diverging lens, well, it doesn't make any sense for it to converge, does it? So what it will do is it will diverge as if it came from the focus. So there's the focus. It diverges as if it came from the focus. So the ray does that, and it appears to have come from there. And then a ray which comes in through the optical center, well, that will also go straight through. So there's our ray. No, it isn't. Ray through the optical center. So the image forms where these rays appear to meet. Now there's only one real ray here, so this is not a real image, it's a virtual image. So here we have a virtual image. It is an upright image, but it is reduced. It is not as big as the object. So there's your single, you'll be glad to hear, ray diagram for the concave lens. I notice that I haven't quite got this right. It should have gone through right here. But the outcome is basically the same. The image would have been slightly different. It would have been slightly smaller, but there it is.